Hello, everyone, and welcome to AWS Storage Solutions for Containers and Serverless session. This is SDG 205. My name is Abrar Hussain, and I'm one of the principal product managers for Amazon Elastic File System, or Amazon EFS. And I'm joined today by Souvik Bhattacharya, who is a senior product manager on Amazon S3. He will be covering the later part of the session. We've got several topics prepared for you today. From an agenda point of view, we're going to give you an overview of serverless and modern applications so you can really understand what we mean by serverless and modern applications. Then we're going to talk about the why of modernizing applications. Then we'll dive deeper into how you can modernize your applications with storage services like Amazon EFS and Amazon S3. We will give you some specific customer examples and use cases so you can decide which storage service to select for which use case. And towards the end, we will provide you a quick summary and give you an overview of some of the other related sessions that you can go attend to learn about serverless and containers at a 300 level and at a 400 level. So let's get started. So we'll do an overview quickly for serverless and modern applications. We launched AWS Lambda over 6 years ago, and we continue to be humbled by how many people have adopted it. Hundreds and thousands of customers have built applications that drive trillions of invocations per month. Now, AWS Lambda may have started serverless, but it's been the builders and developer community that has turned serverless into a revolution on how to build in the cloud. It's been truly amazing to watch that. So when we talk about serverless applications architecturally, one thing that is common with serverless applications is that they follow the same design ideas of the web and the internet. I'm talking about small pieces loosely joined. So serverless applications are modular. They're composed of multiple AWS services and customer-developed components. It is why we are so focused on providing lots of integrations with services like AWS Lambda, EventBridge, Amazon EFS, and Amazon S3. We're going to talk about all of these integrations today. So the idea is we want to make it easy for you to build new applications and functionality through loose coupling with other components, even components that you're building. So that was serverless applications. Let's quickly talk about modern applications. Modern applications describe a new way of developing software that changes how customer value is delivered. Now, modern applications are not static. They're constantly evolving. So when we say modern, we mean what is modern today. So through our own experiences of building Amazon.com and serving millions of customers on AWS, we've observed some common characteristics with modern applications. They're based on microservices architecture. They're modular, they provide granular access, they're based on event-driven programming models, and they provide programmatic governance. So the idea is modern applications reduce scope while increasing focused ownership within the teams. This allows the team to rapidly develop applications because they're focused on the actual code and not managing the infrastructure needed to scale that code. So that's what we mean by modern applications today. So now that we know what serverless applications are and what modern applications are, let's talk about the need. Why? Why do we need to modernize applications? So we're going to cover 3 specific customer benefits that come from modernizing applications. We're going to start with cost savings, right? So companies running their applications on premises typically have to pay for more infrastructure than they actually end up using. And there are 2 main reasons for that. The first reason is they have to dedicate servers for security and other isolated reasons. So the servers are basically sitting underutilized. And then second, they are provisioning compute and storage based on a forecast, which means they have to over-provision, and the servers are still sitting underutilized. So by modernizing their workloads using elastic services that automatically grow and shrink, customers only pay for what they use, and they're able to lower their total cost of ownership. So that's the first benefit, cost savings. The second benefit is the increased agility that comes with this elastic services. Elastic Kubernetes service, elastic container service, elastic file system. They allow customers to instantly scale up and down their resource consumption. This way, the organizations are agile and they can quickly adapt to changing business needs. And then the last and important benefit for modernizing applications is greater efficiency or faster time to market. Companies who adopt serverless applications and modern applications, they also change their processes to go along with it. So instead of spending time on managing infrastructure, which is undifferentiated heavy lifting, the companies and the developers in the company are able to focus on code, and then they can release software faster, release value faster, hit the market faster. Okay, so we talked about why modernize applications, but there's one key thing. Modern applications also need durable shared storage. There are three main reasons why durable shared storage is required for modern applications. Number one is availability and durability. Containers and serverless functions are transient in nature, as you know, so long-running applications can benefit from keeping their state in a durable storage. So if you want your containers and serverless applications, your modern applications to be stateful, you will need availability and durability. And that's what shared storage can deliver. Then the next benefit is data sharing. So distributed applications like web services, machine learning inference, and continuous integration and continuous development, they benefit from a shared layer. And then the third piece is the scalability. So if you're building modern data-intensive applications like analytics, that requires fast access to large volumes of data. So regardless of your application, applications are stateful, right? And applications need durable shared storage, and that's what these benefits are. Okay, so far we talked about what are serverless applications, what are modern applications, why modernize, what are the benefits. Now let's start talking about the how. How do you modernize the applications? We're going to start by diving deeper into modernizing applications with Amazon EFS first, and then we're going to cover Amazon S3 later. So what is Amazon EFS? We launched Amazon EFS, or Elastic File System, back in 2016 to give our customers a super simple, serverless, set and forget, cloud-native Elastic File System. You can get up and running in seconds, and you can create a new file system in as little as 2 clicks, and you can scale that file system elastically to petabytes. It is trivially easy to use Amazon EFS. And Amazon EFS is serverless, so it's ideal for your serverless applications. You don't need to provision or manage any infrastructure or capacity when you're using Amazon Elastic File Systems. So when we talk to customers about moving to and growing in the cloud with EFS, the one thing that excites them, besides how easy it is to use Amazon EFS, is that EFS helps minimize the risk along their journey. Now, why is that? It is super easy to lift and shift your applications onto Amazon EFS. If your applications are using Network File Access Protocol, EFS supports that. So your applications, your developers are using the same interface that they have been used to while running their applications on premises. So that's one important reason why lifting and shifting is easy for Amazon EFS. Then the second part is EFS is highly integrated. EFS file systems can be shared up to tens of thousands of concurrent connections. And these connections can come from any AWS compute service. It could be the traditional EC2 instances, or it could be coming from containers that you are running in your environment on AWS, or containers running in AWS managed services like AWS Elastic Container Service, AWS Elastic Kubernetes Service, or AWS Fargate. You can also access EFS from serverless functions running inside of Lambda. And since EFS is highly integrated, supports full AWS compute integration, you can accelerate your application modernization journey. And once you have modernized, running Elastic Cloud infrastructure results in further development and operational efficiency, which enables you to build and deliver more features and capabilities to your customers at a faster time to market. So let's look at some of the use cases. In the beginning, we talked about, we will dive deeper into specific customer use cases when you can be using EFS for modernizing your applications. So we're going to start with 3 basic customer use cases. The first one is building scalable digital experiences. This involves creating and modification of digital web content. Examples include web hosting with WordPress or Drupal, course management with Moodle, or even building and maintaining corporate wiki pages. Then the next example we're going to look at today is machine learning inference, which involves deploying machine learning models for real-time inference with large libraries or pre-trained models. Common examples include sentiment analysis, image classification, and then search applications as well. And then the last example we're going to look at today is media processing, which includes image processing, video hosting, and video editing apps. So let's find out how you can build and modernize these applications using Amazon Elastic File System. We're going to start by talking about building scalable digital experiences with Amazon EFS and AWS container services. Now, to really understand how to do this, we're going to dive deeper into the architecture, right? So many customers are migrating their existing applications from on-premises and even from EC2 instances into containers to simplify their operations, lower their compute cost, and scale more elastically. And because of EFS integrations with ECS, EKS, and Fargate, even applications that need shared storage can also be migrated. What are the advantages? Well, with EFS, you can persist storage across containers, and you only pay for what you use because it's elastic, and it's a pay-as-you-use model. And then you can create and manage a multi-tenant environment in a cloud-native way because EFS has the native capability of using AWS Identity and Access Management and EFS access points. We're going to talk about what access points are shortly. So let's take a look at a couple of screenshots to understand how easy it is to attach an Amazon Elastic File System to your Amazon ECS cluster. We're going to start by creating an Amazon ECS cluster first. Once you're creating the cluster, you can quickly create a security group for Amazon EFS that allows inbound connections on port 2049. Then you can quickly hop onto the Amazon EFS console and create an EFS file system in just 2 clicks. It will automatically create a file system for you with all the recommended default settings that we have. And then once you have created the file system, you can hop back onto the ECS console and create a task definition, which describes 1 or more containers that form your containerized application. And you can update the task definition using the ECS console or even the JSON, and you can select the file system ID and the mount point to attach your EFS file system to your containerized application. So those are the steps you would follow to attach your EFS file system to your containerized applications. So now that we know how to attach it, let's just look at a bigger picture, right? Let's just take a look at a reference architecture of how you can build a scalable digital experiences using EFS and container services. So we're going to talk about a content management system which uses applications like Drupal and WordPress. And it's basically sharing and uploading content to be used across multiple instances. So applications like this require high availability, high performance, and the ability to share data across container instances, and the ability to scale up or down based on business needs. So how's it all going to work? Visitors browsing the site URL are going to be pointed to an application load balancer, which spreads the traffic to multiple AWS Fargate instances across multiple availability zones for resiliency. And since EFS standard storage classes are regional, they're available in multiple availability zones, and they can be easily mounted to each of those Fargate instances. So EFS file systems are not only highly durable, they're also shareable. So for example, you can update the EFS content from one instance, and you can easily access it from across multiple instances. Now, if you look at this architecture, it is completely serverless. We're using Aurora serverless as well to hold relational database transactions. So AWS Fargate, Amazon EFS, and Aurora is all serverless, giving you an elastic scale, and you only pay for what you use. So we looked at a reference architecture. Let's look at an actual customer example. Acquia modernized their web hosting services using Amazon EKS and Amazon EFS to reduce their infrastructure and operational maintenance overhead. They were able to improve their customer experience by being able to dynamically scale their environments. They lowered their total cost of ownership through elastic file storage and compute utilization. And they were able to reduce their administrative overhead because EFS is serverless and Fargate is serverless. It is fully managed for you. So we looked at how you can attach an EFS file system to your Amazon ECS container services. Next, we're going to look at how you can attach an Amazon EFS file system to Amazon EKS pod. And we're going to be using dynamic provisioning for that. So EFS is integrated with Container Storage Interface, or CSI. So customers can use the CSI driver to create EFS file systems. You can use dynamic provisioning to attach persistent volume to a container on demand, eliminating the need to pre-provision your volumes. So how is this all going to work? So step one would be to create a persistent volume claim. This is done by the user. Once a persistent volume claim has been pushed out, then the next step would be to use the CSI driver to create an access point within the EFS file system, and that is automatically mapped to the persistent volume, which is returned back to the user. Now, each access point created by the CSI driver enforces a unique identity and root directory for that application to ensure that the data is private to just that specific persistent volume. Let's take a look at an example of a customer that is using Amazon EKS and Amazon EFS. Johnson & Johnson. They built their data science platform using EFS and EKS. They're now able to scale elastically, increase their innovation by reducing data analysis time by 35%. And they were also able to reduce their storage cost by 37% because they use EFS one-zone storage classes and EFS lifecycle management that automatically transitions infrequently accessed files to an infrequent access, lower cost storage tier. So next, we're going to talk about the two remaining use cases, machine learning inference and media processing. And for this, we're going to be using AWS Lambda and Amazon EFS. So this is going to be all about Lambda and EFS, serverless compute, serverless storage. So let's get right into it. Customers are building highly durable and available serverless applications by using EFS as a serverless storage, shared storage layer. But why? Why is it important? Well, EFS, like I said, provides petabyte scale elastic storage for your Lambda functions. Previously, Lambda could not operate on data larger than 512 megabytes via temp space that each function instance gets automatically. So with EFS, customers can now operate on larger data sets. So that's the first advantage. Then the second advantage is by saving the state of the function at the end of its processing and loading the state for the next run, you can make your Lambda functions stateful. And then you can also make your applications faster because EFS provides consistent low latencies. With EFS, read operations are as low as 1 millisecond in terms of latency. You can build a fully elastic file system with compute storage that grows elastically, and developers can focus on building applications and don't have to worry about managing their infrastructure. Customers are able to build scalable applications by sharing data across tens of thousands of Lambda connections. So there's absolutely no reason to not use Lambda and EFS in that case. So let's take a look at how you can attach EFS to AWS Lambda. Using the Amazon EFS console, you can easily create an EFS file system with just a few clicks. We have already looked at this. Next thing you're going to do is create an access point. Access point provides application-specific entry points into the EFS file system and data. Why is it important? Well, it's important because with access points, you can synchronize permissions and you can prevent privilege escalation by enforcing the identity of all inbound connections using that access points. So this is particularly useful in serverless applications where there is no first-class notion of a POSIX identity. So that's where access points are super helpful. So once you have created the access point, you can head on to the AWS Lambda console and create your function. While you're creating the function, you can easily add an Amazon EFS file system to your function by selecting the file system ID and an access point. And that's it. You have now attached your EFS file system to your Lambda function. So now we're going to start taking a look at some examples. We're going to focus purely on building elastic applications. So in this example, we're going to focus on building an elastic machine learning inference application. So in this specific example, when you send an image of a signpost that has Chinese language on it to the application for text extraction, the application will return the actual text in the form of a predicted label. Let's see how we can make this work. So we're talking about machine learning inference. Inference is the real-time part of machine learning, and inference required that historic machine learning models data is built and loaded to the function. But the Lambda functions only have a limited temp space, 512 megabytes. So in this case, we're going to upload the historic machine learning model to the Amazon Elastic file system. So that's the first step. We start by loading the models to Amazon EFS. Then the client application makes a request to the API gateway, and it posts the image with the Chinese language on it. Next, we invoke the Lambda function to serve the prediction. The historic model that was loaded into the function, into EFS, is now loaded into the Lambda function. And since with EFS there is no size limit, you can use Lambda for any kind of inference use case. You're not limited by size. The Lambda function uses the preloaded model library to serve up the prediction and return the predicted label back to the user. So one cool thing about this entire architecture is that it is fully elastic. EFS is elastic, Lambda is serverless. You're only paying for inference. When you're not making any predictions, you're not paying anything. And when you're making predictions, you're paying per prediction, or you're paying per inference. So let's look at a customer example. Skywatch. They process satellite images, and it was challenging for them because their images did not fit in the Lambda temp space, and the processing time was also very slow. So they used Amazon Elastic File System to store and process their satellite images. EFS enabled them to concurrently process shared data through a multi-stage image processing pipeline. They were able to accelerate their image processing time because EFS provides consistent low latencies, and they were also able to lower their cost through reduced operational overhead. They were not managing anything on EFS. Another quick customer example I want to share with you is Asurion. Asurion uses Amazon EFS and AWS Lambda for machine learning inference. It is very important for Asurion to provide their customers with great customer service, since it's a customer-oriented business. So they focus heavily on using machine learning to analyze call recordings and make sure that their experts are friendly and are doing a great job in customer satisfaction. So because call volumes could be high and low in a specific cycle, they wanted to use AWS Lambda to achieve the elasticity on the compute point of view and pay as you go. But without EFS, they couldn't have done this because their call recordings were too large to fit inside of an AWS Lambda function. Okay, so as I summarize Amazon EFS and modernizing applications, I want to just quickly recap the 3 use cases we covered. We covered building scalable digital experiences. We talked about machine learning inference, and we talked about media processing. And this is all EFS-specific use cases for modernizing your applications. Next, we're going to look into how you can use Amazon S3 for event-driven and serverless architectures. And for that, I'm very excited to invite Selvig, our X3 product manager, to talk to us about it. Take it away, Selvig.
Thanks, Abrar. That mic's plugged in. All right, so I know I'm wearing a hoodie, unlike sneakers, so I promise you I'm still going to show you some cool stuff, OK? And also, I fully understand that I'm standing between you and dinner. Try not to hold that against me. So we'll talk about Amazon S3 event-driven application. But before that, I'm just going to give you a quick overview of Amazon S3. I'm pretty sure most of you are familiar with what Amazon S3 is. It's the largest object storage system that AWS has. I recently found out that we have over 200 trillion objects. The kind of statistic kind of flies over my head. I don't even understand that scale. So we're going to talk about how you can build event-driven serverless applications that react to changes on your S3 objects. After that, we're going to look at some cool use cases. We'll start with some basic use case, and then we'll move to some of the more higher-level advanced use cases as well. We'll see, like Abrar mentioned, like building loosely coupled applications using Amazon S3 event notifications. And then I'm going to share with you something cool that we launched yesterday. So it's not even been 24 hours since we launched something. So building scalable serverless applications with Amazon S3, for much of the traditional software, building applications would often mean bringing the data layer to the compute layer. This is inherently problematic because for developers, bringing their data layer to their compute layer, when data layer grows exponentially so in the last few years, we have seen data grow ridiculously. They also have to manage their compute scale. This would mean spreading out their compute over multiple fleets in case you hit peak load times, but also not knowing what to do with those fleets when you don't hit your peak loads, right? This is why the S3 to Lambda architecture is so useful, because we are reversing that trend where we are bringing the compute layer to your data layer. And this could be your objects, your files, your databases, or any other sources. And this is increasingly important and useful for developers because now you don't have to worry about your compute scale. Lambda scales up and down depending on your data layer load times. And at your peak load, Lambda scales up automatically. And when you don't need all that compute, Lambda scales down automatically as you go as well. This is super helpful for developers, mainly because you don't need to worry about scaling constraints when you're writing your applications. You can write your application for a single item of data and have that scale across millions or billions of objects. So we think that's super helpful. I'm going to talk briefly about how you can make it happen with S3 event notifications. So S3 has event notifications on a bunch of things that happen to your objects. For example, when you add a new object to your bucket, you can use that as a trigger for a downstream application. When your object metadata changes, something that we launched yesterday, we launched a whole bunch of new event notification. For example, when you add an object tag to your objects, you can use that as a trigger for your events. When your objects get removed throughout their replication journey, their life cycle, retention, and things like that, you can use all of that as inputs for your serverless apps. And you can send them natively within S3 to one of three destinations. You can send it to an SQSQ, you can send it to an SNS topic, or you can invoke a Lambda function. Lambda is what I will specifically talk about today. We launched this feature years ago, and it still continues to be something that we heavily invest in, building new events every single year. Setting up S3 events is super simple. You go to your bucket properties. I'm sure most of you are familiar with this page. You look at your configuration. You look at your events. With the click of a button, you'd be able to click your events. You can filter those events based on prefix and suffix. I'll get into a little bit of detail on why these filters are super important. You can select the events that you need and then send them to the destinations that are important to you, Lambda being the most interesting use case today. So once you have enabled your event notifications, you might be wondering, cool, what do I do with this? The first use case I want to talk about is translating at scale using Amazon S3. Now, organizations that have a really global footprint, providing information for different customers living in different geographies is an everyday reality, right? And this could be product catalog, application libraries, so on and so forth. And there's another use case of translation. When your translation layer builds up over time, when you run analytics on those workloads, you might want to translate back to a single base language for specific analytics. Now, building machine learning algorithms to translate at scale can be super challenging, right? Like, you need to build those machine learning models by training data sets, evolving over time. You need to dedicate specific teams to take care of those data sets and improving your model as your data grows and builds over time. So thankfully, Amazon has a machine learning service called Amazon Translate that can translate up to 54 languages and automatically detecting the source language. And you can use Amazon Translate with Amazon S3 and AWS Lambda to build event-driven applications such as any of the serverless architecture that we'll go through right now. The first one is pretty simple. It's translating in real time. Object lands in S3. That leads to an event that invokes a Lambda translate function that then uses that object to translate based on your translation requirements, drops it back to the S3 bucket, right? This is simple, works great for small documents, smaller in scale. But what happens when you have large documents? What happens when you have millions of documents, right? So that increase in both breadth of your objects and the number of your objects, there comes some scaling challenges. The first one is using Amazon Translate, which has specific service limits. However, S3 does not, and S3 scales up as your data scales up. S3 has almost infinite ingestion rate. So what we do here is we use Lambda to be able to decouple Amazon Translate and Amazon S3. And the way we do that is by adding an SQS queue and a DynamoDB table. So you might be thinking, that's weird. Why an SQS queue? We add the SQS queue to enable queuing, which then makes the Amazon Translate service limits more responsive to the S3 load of data. And we add the DynamoDB table to keep a real-time tracking of the status of your translation, right? So let's see what's happening here. Let's say I have a rather large document that I just can't put to Amazon Translate, right? So I need to do something with it. So I put that document in that S3 bucket. That becomes my batching S3 bucket. When I land that object in that bucket, I invoke a Lambda function. Let's call it a batching function for now. What that does, it deconstructs the big document into smaller chunks, right? And then it drops it into the translation bucket. And as soon as that happens, then we invoke the translation function, which then does two things. First, it adds that to an SQS queue, which generates a message. And second, it adds a trace in the DynamoDB table that your translation is in queue. When SQS receives that message from Lambda, it then starts the translation function that then invokes translate, and then you have the translated text. When you get the translated text, the Lambda gets invoked again, and you can add it to the DynamoDB table. Your translation is complete. And then you can also add the translated object to your results S3 bucket. So what we have done in this scenario is decouple translate and S3 in a way that you can handle multiple documents, millions at scale, and not have to worry about running into service limits. And I'll be happy to answer questions specific to this architecture, but I want to walk you through a few other use cases. The next one that I want to talk about is business workflows. So you can think about a business workflow that an organization may experience on a daily basis is an if this, then that type of a situation. So organizations have complex workflows often embedded within their processes. Let's say a customer processes an order. Let's say your employee requests for vacation time. All of this could trigger automated workflows. I want to show you a really low-code approach of handling those workflows in real time and at scale. Now, this involves three specific AWS services. The first one is, of course, Amazon S3. The second one is AWS Lambda functions. And the third one is AWS step functions. So we'll go through them one by one, but before that, Just want to underline some of the business use cases for this. There could be many different use cases. The first one could be something like, maybe your business automatically pays invoices when your vendor sends you an invoice under a threshold billing amount, for example. Or it could also be your customers submitting a completed form that then automatically books a consultation request. So any managed workflow that takes a document or a form as an input can be really good candidates for this use case. So let's see how this is gonna work. So the first part of that, it's fairly simple. Data lands on Amazon S3, which invokes the Lambda function, right? So the Lambda function is a proxy to start execution with step function. So let's take the document example. You can use services like Amazon Textract to extract specific text from the document to respond to that change. Or you can use Amazon Rekognition to analyze image and process them. Once you have done that, within that step function workflow, the Lambda function would use environmental variables to see what you need or what you want to match is matched by the object in S3. If it matches, it invokes the match function. No prizes for guessing what it does if it doesn't match. So this way, you're able to create a workflow which practically looks like a flowchart drawn on paper, right? But that responds to multiple documents, multiple forms, landing on your S3 bucket at scale without you having to worry about building that workflow, provisioning that capacity, and managing that infrastructure. So I think that's really cool. The third one that I want to talk about is, I think Abrar mentioned a little bit about this use case, but I want to go into a little bit more detail on converting audio into useful analytics. Now, audio inherently is unsearchable, so that's an inherently problematic data type. And we all know that companies have call centers that record these audios, conversations with customers, and then they just sit in an archive, right? So there could be multiple use cases in analyzing that audio. For example, you could run machine learning models to generate a sentiment score for the audio, which could then tell you whether that interaction with your customer was positive, negative, mixed, or even neutral, right? Similarly, you can triangulate that sentiment score with time of day, geography, and things like that to generate insights like witnessing or insights around a problem that's happening at a specific geography at a specific period in time. So we feel using audio as an analytics source is crucial for our customers. And I want to talk about 3 different tools that lets you do that. Amazon S3 by default. AWS Lambda functions also by default. But also we're going to talk about Amazon Transcribe, which is a transcription service that converts audio to text automatically. It has automatic speech recognition. It detects 31 languages and dialects. And it also can distinguish speakers who are speaking in the same phone call. Now, think about what it would take to build this machine learning service from scratch in your own company. It would probably require a small village. So that's why having that transcribe service available to you that you can use whenever data lands in S3 through a simple Lambda invocation is super powerful. So let's see how that looks. Very similarly, MP3 audio files comes with an S3 bucket, right? Which then invokes a transcribe Lambda function. Well, now, what the transcribe function would do is it would convert that audio into text, which would then come to the same S3 bucket. And this is where filtering-based event notification comes in handy, right? If you remember, I showed you how you can create event notification for filtered events. So you can set up your event notification so that it invokes a specific Lambda function when an MP3 file is added, but invokes a different Lambda function when a text file is added. So as a result, when the output of the Amazon Transcribe function here lands on that S3 bucket, it can then start invoking the sentiment Lambda function, which passes it to Amazon Comprehend. Just a quick background. Amazon Comprehend is also Amazon's machine learning service that generates a sentiment score on text documents. You can get an array of sentiment score, like I mentioned, good, neutral, mixed, bad. And you can store those sentiment scores in a DynamoDB table to then understand and analyze data even further. Now I know what you're thinking. You're thinking like, okay, what happens to multiple languages? All right, you may not be thinking that, but I want to show you that use case anyway. So I want to show you how we can also use this same architecture, but modify it slightly when we handle multiple languages. The key to think about multiple languages is while you are running the same services, when it comes back to analytics, you want to come back to a single base language. It's increasingly complex to run different analytics jobs on different languages, so you don't want to do that. So we have modified this architecture slightly. Objects land in S3 bucket, and one of the key ways customers do this is by adding a language identifier metadata to that object. For example, let's say an MP3 file lands on your bucket, and you have added a metadata that it's French audio, right? I'm just going to use French as an example, because why not? So when that French audio file lands on your bucket, it first starts the Amazon transcribe function with AWS Lambda. And it knows that it's a French audio file because, well, it's in your metadata, and it converts that audio into French text, which then adds to your S3 bucket as a JSON file. Now you can set up your S3 with notification to react to JSON files by passing them to a translate function. You're doing this because you want to convert it to a single base language in a text file. And when that text file lands on your S3 bucket, it can invoke the final Lambda function to create a sentiment score that, with Amazon Comprehend, that can go to a DynamoDB table. So let's zoom out a little bit, and let's see what happened here. You used the same audio file with a single language metadata to not only translate that language to French text, but also use it for real-time analytics in English. And I think this is super useful, uses 3 machine learning services without you having to build a single line of code. And that's the direction that we hear from customers like you for serverless architectures. They want to run parallel serverless workflows on single items of data without creating derivative copies. And this will come in even more handy when we talk about something that we launched a couple months ago called Amazon S3 Object Lambda. Anybody in the room familiar or even heard of Amazon S3 Object Lambda? I can't really see much with this light, so I'm just going to assume no. So Amazon S3 Object Lambda is a really cool feature that we built earlier this year that adds Lambda functions in line with the S3 GET request. This is a new capability that lets you add your own custom Lambda code to process data retrieved from S3 before returning to your application. And this automatically processes and transforms your code before getting retrieved by S3. The Lambda function is actually invoked in line with your GET object request. So you don't need to make any changes to your applications at all. So for the first time, you would be able to, for example, run Lambda functions to filter rows, or resize images, which is the most favorite Lambda application of customers' choices, and also redact data, and so much more with S3 Object Lambda. So when we think about these data transformation use cases, customers often take one of these 2 paths. First, when they need to react to different objects and transform them differently based on what their different applications need, the first way they do this is by adding multiple derivative copies of their objects. Well, that's fine. You can have different objects for different applications. But then you have to go manage all these different objects and then figure out their retention, their life cycle, and also their cost. The second way customers often do this is to have stand-up proxy infrastructure in front of their S3 bucket that then processes your objects differently based on what their applications need. Well, I mean, fine. But that's not ideal either, because then you have to manage all of this infrastructure. You have to manage all this capacity. But that's not ideal either as well. So we wanted to build a solution that doesn't need either of these. We wanted to bring that object in line to your application to whatever your applications need with the help of a Lambda function. You will not need to have to build derivative copies or create new proxy infrastructure. So let's talk a little bit about how it works, right? So you have your application, and you want to start with an object Lambda access point. So an object Lambda access point is a typical S3 endpoint that you point your application to. Once your application issues a GET request to an object in your S3 bucket, what Lambda will do is that it will go to that S3 bucket with a standard S3 access point and pull that object from S3. But before returning it to your application, it would transform into whatever code you have used that Lambda function for. So this is super helpful because for the sake of your application, nothing really changed. Your application still issued the same GET request, but it's getting a dynamically transformed response depending on your Lambda function that you have built for yourself. So this is super helpful for customers like Ryanair, who recently built their COVID-19 mobile wallet with the help of Object Lambda. So Ryanair recently had to redo their entire application to validate COVID travel documents according to EU flying laws. So they needed PCR reports, immunization records, and they used S3 Object Lambda to turn around the solution in just under 3 days. So S3 Object Lambda uses the same application, checks in the background whether that application meets the document requirements, transforms them on the fly to make sure it's a PDF copy that EU travel regulations accept, and then returns back to the application. And for the application, it's almost as if nothing changed. And that's the beauty of Object Lambda. That's what customers have been doing, dynamically transforming objects without making any application-level changes. I want to take maybe a 5-second pause to walk through this, but I also want to talk about something that we launched yesterday. So before we jump into the launch, I want to dial back to a quick slide similar to what Abrar mentioned at the beginning, is why customers build serverless applications. Serverless applications, loosely coupled, great stuff, object changes happen, those invoke downstream applications, great. We want them to look like this, object changes, downstream applications, great. But often they end up looking like this. And they look like this because we often need a single object change to trigger multiple applications downstream. Often we have multiple objects that need to react to a single application. So that's not really pretty or helpful. And when we see customers reacting to these kind of needs, we see them building single-use mechanisms like this. So this is from a customer that I spoke with who needed a single object to drive changes to a translate function, add a record to a DynamoDB table, start an EC2 instance, and also build a step function workflow with a single object. And this customer was hell-bent that I am not going to create multiple copies of the same object. So what they did was they built an SNS bridge where the object invokes SNS with S3 with notification, which is then subscribed by 3 different Lambda functions and also an SQSQ. Now, think about how complex that is. You have to manage 3 different Lambdas just to drive a single application. So we saw this, and we thought it could be made simpler with Amazon EventBridge. So Amazon EventBridge is AWS's central event management hub, and we are really happy to have S3 event notifications natively within Amazon EventBridge. So let's think about why and how it helps. So first, EventBridge helps fanning out. So each object event within an S3 bucket can trigger up to 5 different applications. So think about an audio file that needs to start a transcription service, a translation service, and a Dynamo table change. You can do this all within a single rule, which we think is really, really cool. It reduces infrastructure. It reduces complexity in the serverless architecture. The second key benefit is EventBridge's industry-leading pattern matching capabilities. S3 buckets can fill up pretty quickly, right? Customers have millions or billions of objects, and they often tell us that, hey, I really want to build my serverless applications. I want to, dip my toes in the serverless world, but I want to make sure that it's not invoking millions of Lambda functions, right? And this is where EventBridge comes in really, really handy, where you can set up rules so that your Lambda invokes only when your objects match that rule. For example, you can match based on any parameter of the entire event payload. Let's say you only want to invoke a Lambda function if your objects are of a certain size. Let's say you want to invoke a step function when your objects are created after a particular date. All of these are different use cases that I've heard from customers. So you can do that with pattern matching so that you're only paying for the events that you need, and you're not paying for events that are generated that are not going to a target destination. So we think that will help really make this solution cost efficient for our customers. And finally, EventBridge also lets you archive and replay past events. And you might be thinking, like, OK, I've already invoked my destinations. Why is this important to replay these events? So this is important for 3 different use cases. Like first, for example, you may have found a bug in your code that have led to some of your events not triggering your applications. And to keep parity, let's say you want to redrive those again. So you can replay those events. And you can replay those events at any time frame, starting at 1 second to as much time as you need. The second use case where I think customers would love replay is when they are hydrating their existing objects to a new application. Think about your S3 bucket with millions of objects already existing, and now you want to create thumbnails of those objects. So you can redrive your past objects and use that same Lambda function without having to worry about creating new ones. And then finally, replay is also super helpful to debug failed events. So if you have event notifications that you wanted to receive but did not, replay gives you a history and maintains that archive of events that you can then use to make sure that your event-driven applications are reacting as they should. Now, setting up EventBridge with S3 is really, really simple. We made it as easy as clicking a checkbox. You use the same event notification page, and you turn on Amazon EventBridge for your bucket. Once you have turned this on, you can go to Amazon EventBridge and create the rules that you need. You can create events for a specific type. You can have multiple event types, and you can pattern match with EventBridge's pattern matching system. So we think this is going to be super helpful for our customers to take their serverless application to the next level. And now I want to focus on what do you do after you have built your serverless application? How do you diagnose and increase your observability? And to do that, I want to talk about 2 specific tools. I want to talk about AWS X-Ray for diagnosing serverless event-driven applications. And then I also want to talk about S3 Storage Lens that helps you monitor your overall S3 usage. So first, AWS X-Ray gives you end-to-end context propagation. That's a tough phrase, but I'm going to just share briefly what that means. AWS X-Ray lets you check your S3 requests throughout the entire request lifecycle. So you would be able to diagnose problems, bugs throughout the entire request journey across different microservices. So when Abrar was talking about a good serverless architecture is multiple microservices that are loosely coupled, AWS X-Ray gives you the tools that you need to diagnose those services and make sure that they're working as you want them to. For example, you can check for higher than usual latencies across each node to understand where problems in your serverless architecture occurs and then take actions accordingly. So we think this will be super, super helpful. X-Ray also has a cool feature called service maps that lets you see the relationship between Amazon S3 and other services, such as EC2, in near real time. Now, the second tool that I want to talk about is S3 Storage Lens. Anybody heard of S3 Storage Lens? OK, cool. So S3 Storage Lens is a quick dashboard that gives you a ton of details about your S3 storage. Let's say you want to answer questions like, which buckets in my application are growing the fastest? How is my request analytics like? Do I have the right retention policies? Are my non-current versions managed well? And you can get answers to all of those questions with S3 Storage Lens. And the final piece that Storage Lens really helps you out with is giving you contextual recommendations that are tailored to your S3 storage usage. So we think customers would really, really like that feature. Now, first, as you can see, S3 Storage Lens gives you a quick snapshot of your overall S3 usage. You will see 3 main sections. The first will show you the summary of your storage. For example, here we see this account has roughly 55 terabytes of data spread over 7 accounts and approximately 80 million objects. Then Storage Lens can also give you recommendations based on data protection, security, and cost optimization. The recommendations are so many, I couldn't even fit them in the screen, and they're a little bit pixelated. So we think this is super helpful for customers to really understand the storage, get insights, and take actions based on those insights. So that brings us to the end of the session today. So I want to tie it up with a quick summary. Abrar walked us through modernizing application and why loosely coupled applications are the way to go. Then we talked about using Amazon EFS for serverless applications that need serverless elastic file system. And we talked about some use cases such as content management. We talked about machine learning inference and media processing. We talked about S3 Object Lambda that lets you have your application get transformed data without making any code change. We talked about building event-driven applications with Amazon EventBridge. And finally, we went to some of our observability use cases with AWS X-Ray and S3 Storage Lens. I want to push you to also attend some of our other EFS sessions. I'll leave the screen for a few seconds if you want to take a picture. But I want to highlight that we have a few 200-level sessions like this one that gives you high-level ideas of our serverless concepts. But we also have 300-level sessions and 400-level sessions that you may want to attend for more stronger deep dives. Similarly, for S3, we have sessions all across, such as best practices, cost optimization, and also performance within your Amazon S3 storage. I know we are almost out of time, but I want to take a few questions. Abrar and I would be hanging out here. So if you have some questions and you want to ask us a few questions, feel free to go ahead. And thank you so much for spending almost an hour with us today. And I'm really happy to see you here. And I hope you get a really great dinner. And we'll be sticking around on the sidelines.